Hi, welcome back. You may recall last year in calculus we learned an integration technique called U-Substitution. Simply put, that's where we replace all the x's with u. We can do something similar for multivariable calculus, for double and triple integrals. The biggest difference is that instead of converting a single variable, we are going to convert an entire region. So today, it's really about the region we are projecting to the function. So we're going to try to rewrite the region. This is similar to what we've already done to converting polar, cylindricals, and spherical from rectangular. However, we did not always go into the detail. We're going to come back to a lot of these later on. Here are some examples. Determine the new region S. Now remember, so if I'm given a double integral, it has a region R. We are just going to convert R to another domain S. So that's going to be our substitution. So today, though, we are only going to replace the domains. Tomorrow, we're going to take a look at how we can rewrite the entire integral. So today, we're only going to be worried about how we can change our base region, the domains. So we're given this ellipse. Our region R is this ellipse. X squared plus y squared over 36 equals 1. The transformation or the substitutions are given as follows. X is u over 2 and y is 3 times v. Now, how we come up with these equations is a little bit more complicated, but for right now, we are going to be given the transformation, and these are our substitution. Now note, since we are subbing for both x and y, as a result, we're going to have both u and v, so two variables. X becomes our u substitution, and y is like our v substitution. And if I plug my base in, remember this is my domain here, this is my base, it's an ellipse, but if I plug my substitution in, x, where x is u over 2 squared, plus this becomes 3v squared over 36, we're going to equal to 1. If I simplify this, we get u squared over 4 plus, again, this becomes 9v squared over 36 equals 1, which if I simplify this, u squared over 4 plus v squared over 4 equals to 1, or u squared plus v squared equals 4. Now notice, our new base is a circle. So the new base is a circle. And circles are much easier to integrate than an ellipse. So we can substitute this circle for this ellipse. And that's what we're going to do. In other words, we're going to sub in the circle for the ellipse. So let's see what that would look like then. Why we like this? Well, if I graph the circle, it has a radius of 2, and I can go all the way around. Well, remember, we're in terms of u and v right now, so we're going to let u's be our x's again, and v's be our y. If I write the equation of the circle, it's going to be v equals the square root of 4 minus u squared. If I draw my vertical rectangle, my change in v for my limits, v is going to be between negative square root of 4 minus u squared and positive square root of 4 minus u squared. Now they may not look any easier than our ellipse, but remember, since this is a circle, of course my u is going to go from negative 2 to positive 2. So, but remember, since this is a circle, I could also use polars. And if we look at polars, remember, it's r theta. Well, r just goes from 0 to 2. Theta now goes from 0 to 2 pi. And that is going to be much easier for us to use than trying to do our ellipse. So the whole idea is to make the base easier to work with. It's just like with U-substitution. Make the function easier to integrate. So we just changed. So if you think about what we did like last year when we had our domain from, let's say, from A to B, we just changed our domains. Instead of our domains being in terms of the ellipse, our domain is now in terms of the circle, and we can use polars to make it a little bit easier for us. So let's take a look at another example. R is bounded by the following line: y equals negative x plus 4, y equals x plus 1, and y equals x over 3 minus 4/3. And here they give us a transformation. Again, how they came up with these equations, they did that. We're not going to worry about that just yet. So they're telling us x can be defined as 1/2 u plus v, and y can be defined as 1/2 u minus v. So before we substitute, let's get the region R. So I'm going to graph this. Our first one, y equals negative x plus 4. So 4, there's our first line. Goes on forever in both directions. Next, x plus 1. There's 1. There's x. And the last one is negative 4/3 x over 3 minus 4/3. Alright, so here we are at negative 4/3, and it's x over 3, so it's not a very big steep one, so it's going to go basically up here and crosses at the 4 again. And there we go. So our region we're looking at is in here. Now notice, if I try to integrate here, if I try to integrate this one, I will have to break this up. This will have to be broken up. If I try to do a vertical rectangle, take a look here, line over line, but once I get to the intersection, I have to change lines. So to integrate this one, in other words, to get the area, we would need to use two integrals. And that's kind of complicated. So let's see if there might be an easier way to do this. So let's go ahead and do our substitution. Now substitute and sketch the new region. So let's see here. Well, my first line is this y equals negative x plus 4. So let's substitute it in. Y, we're told, is 1/2 u minus v equal to negative x, negative 1/2 u plus v plus 4. Simplifying here, we get 1/2 u minus 1/2 v equal to negative 1/2 u minus 1/2 v plus 4. Let's see here. Oh, the v's cancel. If I come over here, we just get u is 4. Oh, that's much easier already, because remember, u is my x. U is x. All right, so u is just 4, so that's like a vertical. This is a vertical line. Already, I know this is going to be a little bit easier than dealing with slanted lines. So let's do the next one. Well, the next one was this y equals x plus 1. Well, let's plug in here. We get 1/2 u minus v equal to x, 1/2 u plus v plus 1 this time. Simplifying, 1/2 u minus 1/2 v equals 1/2 u plus 1/2 v equals 1. And notice here the u's cancel, and when you solve here, you're going to get v equals negative 1. And remember, v is like my y, so this is like a horizontal line. Again, already easier to work with. Now, when they chose their u, now you can pick any substitution you want, but you remember this time your substitution has to be in terms of u and v. So your substitution has to be in terms of u and v this time. Last year it was just u. This time it has to be in both. So x has to be a function of u and v. Y has to be a function of u and v. Now, How do they get these to make them work out so nicely? Takes a little bit more practice. We're not there yet. So the last one, we get y equals x over 3 minus 4 over 3. And let me see here. Let's see here. This is what? 3y equals to x minus 4. So let's use that. So if I plug in my y, what do we get here? 3/2 u minus v equals 1/2 u plus v minus 4. Distributing, we're going to get, whoops, that should be v right there. 3/2 u minus 3/2 v equals to 1/2 u plus 1/2 v minus 4. Solving for the u's here, bring over the u. We get u minus 2v, or not 2v, equals negative 4. And then I'm going to solve for v, because remember v is like my y, so v would equal 1/2 u plus 2. Really ugly there. All right, now they want us to graph the new region, so let's go and take a look here. Remember, there's my u, and there's v. If I graph the first one, u is just 4. V is negative 1. And then we have the line 1/2 plus 2. So there's 2. There that is. And so the region is a little bit easier to work with. So if I want to find my limits now, if I go a vertical rectangle here, if I start the vertical rectangle, my change in v starts at negative 1 and just goes to the line, or this line is 1/2 u plus 2. So up to 1/2 u plus 2. My u's, therefore, would go from, well, I got to find out where they meet here. So I do have to find out where they meet. And they intersect. I can continue the line down here. When v is negative 1, my u is negative 6. So it starts at negative 6 and goes all the way to 4, where they meet. So it can go right and left. And there's our limits. And these limits are easier. Even though it's a little bit more work, the limits are going to be easier than dealing with this base here, where I have to split up an integral, especially when we have to solve it. All right, go into video number 2. We'll take a look at a couple more examples. I'll see you then.